Let's look at the traveling salesperson's problem. Okay, it is related to the problem of finding a Hamiltonian cycle in a graph. So given a rated graph G, we want to find a minimum height Hamiltonian cycle. So Hamiltonian cycle because we want to pass through all the vertices. Okay? So if we think the vertices in a weighted graph as cities and the edge weights as distance, the traveling salesperson's problem is to find the shortest route in which the salesperson can visit each city one time, starting and ending at the same city. Okay, so we don't need to pass through all the edges, but we want to pass through all the vertices. Okay, and we want to find the shortest Hamiltonian cycle. Alright, so let's look at our first example. We want to find the shortest Hamiltonian cycle starts at A. So here we have A, B, C, D. We have 4 vertices, okay? So for a cycle, we start with A, and we end at A. And in the between, we have 3 boxes. We want to fill with B, C, D. Okay, so the first box, we have 3 choices. Second box, 2 choices. And then last but 1 choices. So this is like 3 factorial, and which is 6. So we have 6 possibilities. Oh, let me see whether I can move this guy to the left. Okay. Then I have more space here. Okay. Alright. So we have 6 possibilities. Oops. Let's make a table here. So we want to have the Hamiltonian cycle. So let's say we have A, B, C, D, A, B, switched C and D, so D, C, A, C, B, D, A, C, switch B and D, D, B, A, and then we have the D go first, B, C, A, D, C, B, A. Okay, so those are all 6 possibilities, and let's find the length. Okay. A, B, C, D, A. Okay, that's the rectangle. So 2 plus 3 plus 3 plus 2. Wow, that is 10. Okay, and then next, A, B, D, C, A. So A, B, D, C, A. Okay, A, B is 2, B, D, 11. DC 3, CA 11. So that gives us 22 plus 5, 27. Okay, and then we have AC, BDA. So AC, BDA. Alright, so AC is 11. CB is 3, and then BD 11. DA is 2. So we also get 27. Okay, and then next, ACDBA. ACDBA. So AC 11, CD, CD is 3, DB 11, and then BA is 2. Oh, okay, we also get 27. And then A, D, B, C, A. So that's 2, 11, 3, 11. That's 27. Okay, so we go through all the possibilities. Next, A, D, C, B, A. So A, D, C, B, A. A, D, C, B is 2, 3, 3, 2. Okay, that's 10. Oh, do you see these 2 guys? They are smallest. Okay, so this is the shortest. Oh, we should say shortest length. Okay, and And actually, those two, we get the same cycle, right? It's just like one is going counterclockwise, the other one is like the reverse path. Okay, so those are the two. So this guy and this guy, they're the shortest path, Hamiltonian cycles. So far, so good, everybody. Okay, next. So I hope you can try this at home, okay? So you can please work on this problem and pause the video here. And are you done? Let's check our work. So we have the same graph, but just the weights are different. Okay, so we still have 6 possibilities. What are those 6 possibilities? We have a... Let me still use the small letter. Okay, let's see whether I can be lazy and just copy this guy here. So I can... Oops. Okay. Let me see. Alright, let's see. Okay. It's working. Great. Copy and paste. I hope you don't mind. Okay. Alright, good. Let's continue. So here we have the Hamiltonian cycle. And here that's the length. Okay. So first, A, B, C, D, A. A, B. Oh, you see? It's a little bit different. The vertex change. A, B, C, D, A. A, B, 20. B, C, 30. 12. And then 35. Okay, 50 plus 47 is 97. Okay? Next. A, B, D, C, A. Alright, that's 20 plus 34 plus 12 plus 42. What is that? 54 plus 12, 66, 108. Right, everybody? Alright, let's continue. A, C, B, D, A. AC, 42, 30, 34, 35. Ooh, big number. So 72, 106, 141. So far, so good, everybody. Okay, next. A, C, D, B, A. Alright. Okay, so that is 42, 12, 34, 20. Actually, you can see there are 6 cycles here, and actually half of them is kind of the reverse path of the other half. Okay, so what is this guy? 42, 12, that is 54, and then plus 34 is 88, 108. Oh, okay, so you can see this two, they're like the path, but just reverse order. And then next we have AD, B, C, A. So 35, 34, 30, 42. Did we see this before? Yes, here. It's the same thing, right? So we get 141. And finally, ADCBA. That is AD 35, DC 12, 30, 20. And our answer is 97. So, oops, these two are the shortest. Okay, they're just reverse direction. So far, so good, everybody. Okay, so this is how we find the shortest Hamiltonian cycles. We list all the possibilities and we compare and we find the shortest one. So far, so good? Okay. Next example. Showed in the following graph the Euler cycle and a Hamiltonian cycle that are not identical. Okay, remember Euler cycle means we pass through all the vertices and all the edges, but we visit each edges exactly once. Okay? And Hamiltonian cycles, pass through all the vertices, but no repeated vertices, except the starting and the ending vertex. Okay, and the Hamiltonian cycles does not need to pass through all the edges. Okay, so first let's look at the Euler cycle. So let me label them A, B, C, D, E, F, G. Okay, let's just look at the graph and see. Okay, we want to A, B, C. Oh, we can walk this way. See? This way, we can go through the path, walk through the graph. Okay, so we can find the Euler cycle by inspection. What we do is A, B, C, D, B, G, D, E, F, G, A. So this is one Euler cycle. So far, so good, everybody. And can we find more? Of course. If we erase, we can try A, B, G, D, C, and then wrap around, right? So this is A, B, G, D, B, C, D, E, F, G, A. There could be more. Okay, just be patient and look at the graph. So there are multiple answers for this problem. How about a Hamiltonian cycle? Okay. Okay, so let's see here. Hamiltonian cycle, well, the easiest one. Just this square. It passed through all the vertices. Right? So that's A, B, C, D, E, F, G, A. Right? And keep in mind, Hamiltonian cycle doesn't contain all edges. Okay? You just need to contain, so it has a pass through the vertices exactly once, except the beginning and the ending vertex. Okay, so far so good. Can you find another Hamiltonian cycle? Actually, we can't. Why? Remember first, we can look at the vertex with degree 2. Well, this guy. And then the edge adjacent to that vertex must keep them. So this gives us only one choice. So far, so good. So there is only one Hamiltonian cycle for this graph. Okay, let's continue. So here, I make a comparison for you about the Euler cycle and Hamiltonian cycles. So let's go through it. Isn't it nice? Yes. Okay, let's look. For Euler cycle, definition. Euler cycle contains every edge exactly once without repeating. It includes all the edges and the vertices of G. Hamiltonian cycle contains every vertex exactly once, except for the beginning and the ending vertex. Okay, so it includes all the vertices, but does not need to include all the edges. Okay, what's the difference? Euler cycles pass through all the edges. Hamiltonian cycle may not pass through all the edges. And then the Euler cycle might pass through a vertex more than once. Okay? And the Hamiltonian cycle passes the vertex once, except the beginning and the ending vertex. We pass it twice. Okay? I don't have enough space, so that's why this is what I mean. Except the beginning and the ending vertex, we pass through it twice. And then the rest, the outer vertex, just exactly once. Okay, the number of the Euler cycles. So both of them, we can see the graph might have no Euler cycle, one Euler cycle, or two Euler cycles. Or the Hamiltonian cycle, it could be 0, 1, or 2. Okay? Alright. Next, criterion for existence. G is, so the criterion for the existence of Euler cycle, we have a theorem. A graph has an Euler cycle if and only if the graph is connected and every vertex has an even degree. Okay? But for Hamiltonian cycle, we don't have a verified, necessary, and sufficient condition for the existence of Hamiltonian cycle. Alright. Degrees of the vertex. Each vertex must have an even degree. Okay, this is each vertex in the graph. Okay, the degree of the graph. And for the Hamiltonian cycle, each vertex must have a degree of 2. This degree is the degree in the Hamiltonian cycle. Okay, the degree in the graph might be more than 2, but within the Hamiltonian cycle, the degree of each vertex must be 2. Okay, next, how to show no existence. Well, we find a vertex with odd degrees, then we can show there's no Euler cycles. Okay, and then for Hamiltonian cycle, well, we introduce two methods in general. If the vertex doesn't have a lot of degrees, then we can look for the vertex with degree 2, and then the edge incidence must be in the Hamiltonian cycle. Then we can extend, go to the next vertex, eliminate the edges to make sure every vertex has degree 2, and then try to see whether we can get a contradiction. Contradiction means maybe you delete all the edges connecting a vertex, then we cannot reach that vertex. But for Hamiltonian cycle, we have to pass through all the vertices. Okay, next. Relation between the number of edges and the number of vertices. Well, for any graph, so this formula is true for any graph. Okay, no matter the graph has a Euler cycle or Hamiltonian cycle or not. So this formula is for any graph. Okay. And for the Hamiltonian cycles, we know that the number of edges equals the number of vertices in the Hamiltonian cycle, right? Because remember, you have the vertex, edge, vertex, S, vertex, edge, and then this guy is the starting vertex. So that's why we have the same number of edges and the same number of vertices. Or I can use another way to show you. Okay, so, or you can use this way, let V be the vertices in the Hamiltonian cycle. So list them as V1, V2, V sub n. Then in the Hamiltonian cycle, degrees of those Vi's equals to 2, right? And then, So when we use this formula, sum from I to n degree of vi, well, this guy is, because each guy we have degree 2. So this is just like sum I from 1 to n of 2. So this is like 2 plus 2 plus 2, and we have we have n copies of 2's adding together. So that's why it's 2n, and we also know for any graph, the sum of the degrees equals 2m. So that's why both sides divided by 2, we get m equals n. So this is another way to show it. Okay? And how about for Euler's cycle? So Euler's cycle, we know the degrees of all the vertices is not 0 because G is connected. Because G is connected, every vertex there must be at least one edge connecting it, right? Otherwise, it will be an isolated vertex and then G is not connected. Okay, so degree of Vi is not 0, and we also know all the degrees is even, because they're even numbers and it cannot be 0, it cannot be negative numbers, which means the degrees of Vi must be greater equals 2. So it's either 2 or 4, etc. Okay, so that's why the I from 1 to n of the degree of Vi, because each of them is greater equal to 2. So when you add them all up, and here we have n copies of 2, so that's 2n. And for all the graph, we know the sum of the degrees equals 2m. So divide both sides by 2. Dividing by a positive number won't change the inequality. So we get m is greater equal to n. So the number of edges is greater than or equal to the number of vertices. So far, so good, everybody? Okay, so this is the comparison between Euler cycle and Hamiltonian cycles. So I hope you have an idea. Also, it's good to keep this example in mind. This example, we have couple Euler cycle, and we have only one Hamiltonian cycles. Right, and I think there is example we did in the before. Okay. So this example, we have Hamiltonian cycles, but we don't have Euler cycles. There are other examples that we have an Euler cycle, but we don't have a Hamiltonian cycles. Okay. I can also try to give you an example that has Euler cycle but no Hamiltonian cycle. Let's get to the end to have more space. Alright. Okay, let me use a different color here. Okay, so look at this example. We have some graph. Look like this. So this is A, B, C, D, E, F, G, H. It has a Euler cycle. The Euler cycle is like this. Okay, this is an Euler cycle. However, it does not have a Hamiltonian cycle. Why is that? Look at the vertex with degree 2. So actually, A, E, G, H. Sorry, this is D. EB, all of these vertex has degree 2, which means we need to keep all the edges. But then the degree of C and F is going to be 4. So that's why no Hamiltonian cycles. So now we have seen examples that has Euler cycle but no Hamiltonian cycle. We also see examples that has Hamiltonian cycles but no Euler cycles. So there are different concepts. So I hope you, through this comparison, you can understand them better. If you have any questions, feel free to ask me. Have a nice day. Bye.